Hi, my name is Deepak. I'm a software engineer at Google. And I'm going to talk about finding hidden headrooms in saturated clusters. Before I jump into the topic, like I said, I work at Google and I work in Memory Store. And as part of that, I get to work with a bunch of customers who have Valkey in their production setup. And I get I also have got the opportunity to contribute a few things to OSS. And along the theme of keeping things boring and predictable, I'm going to talk about the CPU utilization related metrics that we introduced. But before we get there, I want to talk about the motivation for that. And here in this slide, I talk about the Valkey threading model, which sets the context for the problem. So in Valkey, most people might already know, Valkey has two main threads, or there's a main thread and there is IO thread, and there are other threads like background threads or child threads, which are part of the fork. And to understand the responsibility of each of these, the main thread is the core of Valkey. So it is the one that keeps Valkey functional, right? So with the main thread is responsible for primarily accessing the data structures and serving the processing the commands. So this could be sets, gets, or any other commands that you execute on Valkey. And the main thread is also responsible for delegating work to the IO threads, and it is also responsible for determining how many IO threads should be activated. Similarly, the main thread is also responsible for doing periodic things like rehashing the hash map data structure, or running defragmentation, or doing things like evicting clients which are over the memory, or evicting keys which have expired, right? So the main thread alone is sufficient to keep the Valkey process functional. And IO threads are going to support doing certain things like the IO operations, like the name suggests. And IO threads are responsible for even parsing the query buffers. They read and write to the sockets. And they also take care of doing the system calls, the epoll calls, which listen to the socket events that happen on Valkey process. In the context of this talk, I'm not going to delve into the background threads and the other threads. So let's focus on the IO threads and the main threads. And the main thread, another important detail is that main thread has a ring buffer for each IO thread, and that's how it delegates work to the individual IO threads. Okay, now coming back to the topic at hand. So this goes back a year back when me and my colleague Sumit, we worked on understanding what is the capacity of a single node when it comes to how much throughput it can handle. And we were doing this experiment on a single node with 4-core machine. And what we found was pretty interesting. So ideally, you would expect the relationship between the QPS and the CPU to be linear or close to linear, right? But what we found was something very different. As you could see here in this graph, we saw that the CPU utilization went up to 400%, which is for 4 cores, at about 300K QPS. And then we continued to drive throughput on that node, and it was able to absorb more of the QPS. And this was interesting, right? And we wanted to understand what's really happening under the hood. And when we deep dove into the code, what we found was that busy polling was the culprit. And when I say busy polling, what I mean here is that CPU is actively spinning, waiting for a certain criteria to be satisfied to proceed to the next step. And to understand this further better, the IO threads, as you know, it has a single ring buffer that it looks at to see if there is more work to be executed. And it would busy poll on that, on the queue, the next item in the queue to be present so that it could execute the work. And we found that the IO thread spent a good chunk of the time busy polling, and that was what was surfacing as 100% CPU utilization for that thread. And another interesting thing was it wasn't just the IO thread, but the main thread was also doing the busy polling. The main thread was busy polling, where it would delegate the epoll system call to one of the IO threads, where it would listen for socket events. And until that IO thread executed that epoll, it would just busy poll waiting for it. Similarly, it would also look at the list of pending IO operations for individual clients to see if any of them have completed to proceed to the next stage. And there also, the main thread would iterate over that list actively and in an event loop. So we identified these as the reason for why the CPU would shot up to 100%, even when there is effectively more capacity left on the Valkey process. So in order to understand this better, we wanted to add observability into this. And the way we did that was to add metrics that would tell us what is the time each of the threads spend doing real work by excluding the work that is spent spinning in cycles, busy polling, basically. And then we reran the experiment. We reran the experiment, and what we found was that, as you see the blue line in this chart, it is more close to the linear relationship that we were expecting. And the blue line here is basically the sum of active time of individual threads doing real work. And another interesting thing to note here is it aligns with our story, right? At about 300K QPS, you could see that all the IO threads are active or just active. So it means that at that point, there is enough workload to activate all the IO threads and also to keep them busy polling so that the CPU reaches 100%. So the red line you see here is at 400% soon at the point where the last IO thread becomes activated, which is at about 300K QPS. So if you are looking at a production instance and you're monitoring it, and you see that your CPU utilization is 100% and you provision the resources, you could potentially be provisioning 2x the capacity, because the real 100% capacity is at 600K QPS, which is 2x of 300K. So you could be provisioning by 2x. So this is what the metrics tell us, and that they give us that observability. I would also take this opportunity to talk about a few other improvements that are done along this line in Valkey 9.1. I came across this while going over the pull request, and Valkey 9.1 has done a decent amount of improvement in terms of uniformly distributing the work across the IO threads. So if you look at this diagram here, the main thread would pick which IO thread to assign individual tasks to, which meant that the individual IO thread could be skewed in terms of how much work it is executing. And some of the IO threads, even when active, might be underutilized, and they would be busy polling. So the Valkey 9.1 has improved this by adding another intermediate queue, which the IO threads would poll from to help uniformly distribute work. And similarly, like I talked about, the activation criteria, if we prematurely activate the IO threads, it would mean that it would start busy polling and contribute to the CPU utilization. So we have Valkey 9.1, we have revised the activation criteria for the IO threads. And also there are other optimization for how the main thread efficiently utilizes CPU. I think that's about it. Any questions?